Good afternoon, friends. Now we are discussing viscous resistance of journal bearing in module number 3, that is fluid dynamics of the subject fluid mechanics. So we are considering a shaft here of diameter capital D. So radius is capital R here, rotating in a journal bearing. So the shaft is rotating between the two sleeves of the journal bearing. So the sleeves are taken for a length of L. So the clearance between the shaft and the bearing is filled with the viscous oil. So the shaft has to get rotated in this journal bearing which is filled with viscous oil. So now the oil film is in contact with the shaft. So it is rotating at the same speed as that of the shaft. So while the oil film in the contact with the journal bearing is stationary. So the shaft is rotating at the same speed, right? While the oil film which is having in contact with the journal bearing is stationary. Only the oil having contact with the shaft is also rotating. So there will be a viscous resistance offered by the oil to the rotating shaft. So let capital N is the speed of the shaft in rotations per minute. So then T is the thickness of the oil film between the bearing and the shaft here. So sleeve and the shaft. So it's filled with the oil for the thickness of small t. So L is the length of the oil film or the length of the sleeve for which this shaft is getting rotated. So now the angular speed of the shaft. So will be taken as 2 pi n by 60. So for one rotation, the angle covered is 2 into pi, that is 360 degree. For n number of rotations, it is 2 pi into n. So rotations per minute, it is n. So divide by 60. So will give you the angular speed in seconds. So now the tangential speed of the shaft V, capital V, is given as this speed, angular speed into the radius. So angular speed is 2 pi n by 60 into radius is d by 2. So finally it is pi dn divided by 60. So this 2 pi n divided by 60. So this is giving the angular speed. So this angular speed will be multiplied by the radius, will give the tangential speed, that is along the shaft which is getting rotated. So the thickness of the oil film is very small. So velocity distribution in the oil film is taken as linear. So we take du by dy, that is so differentiation of u with respect to y. So that is differentiation of v with respect to t. So du is change in velocity. So we assume that the shaft is maintaining the same speed v. So and t, that is the thickness distance between the shaft and the bearing. So it is now v by t. So pi dn by 60 into t here. So the shear stress in the oil is given as tau is equal to mu into du by dy. So du by dy, velocity gradient in the shear stress equation. So pi dn by 60t we are going to substitute. Then shear force is now shear stress tau into area of the shaft. So shear stress we are taking what we derived here, area of the shaft. So taken pi into d as the width and L as the length of the shaft. So here, so pi d into L, substituting and simplifying, we are getting shear force. Now the torque required to overcome the resistance of viscosity T is equal to shear force into radius. So because torque is nothing but twisting moment, it is the product of force into distance. So we know the shear force and we know the radius, so d by 2. So we are getting the torque required to overcome the viscous resistance. The power absorbed in overcoming this viscous resistance P is equal to 2 pi nt by 60. So we have T here, torque required. Substitute T and simplify to get the power absorbed or power required in overcoming the viscous resistance in case of journal bearing. So that is viscous resistance of journal bearing. Then footstep bearing. So we have here the footstep bearing shown in the figure. So here an oil film is used between the bottom of the shaft. So at the shaft bottom I am filling the oil here, right, and the bearing, so to which will reduce the wear and tear. So the viscous resistance will be offered by the oil to the shaft. So now we are considering here an elementary ring inside the shaft of radius smaller. Capital R is the radius of this entire shaft. We are taking an elementary ring small r. The thickness of that elementary ring is dr. Now n is the speed of the shaft here in rotations per minute. T is the thickness of the oil film. Capital R is radius of the shaft. So angular speed of the shaft as we have earlier, and tangential speed of the shaft as we have earlier. So 2 pi n by 60 into radius. So here velocity distribution of the oil film will be taken as linear. So the velocity gradient we are taking du by dy as we did in the journal bearing. So and substituting du by dy in shear stress equation, we are getting shear stress now. So shear force is now shear stress multiplied by area of the elementary ring. Area of the elementary ring is now circumference into thickness. So circumference is 2 pi r into dr. We are getting the shear force equation here. Now torque required to overcome the viscous resistance dt is equal to force into distance of the elementary ring. So from the bearing. So that is here R. So we have dt here. So the total torque required to overcome the viscous resistance is integration of dt with respect to 0 to capital R. We are getting T, torque. So power absorbed in overcoming the viscous resistance P is equal to 2 pi nt by 60. So T will be substituted to get the power required to overcome the viscous resistance. Thank you, friends.